I appreciate the opportunity to address you all today. Welcome to all of you for joining us in today's Tech Talk, How Accurate is Your Lateral Analysis? Our format today is going to be different than our typical webinars. Typically in our webinars we have a long presentation and a short Q&A at the end. This Tech Talk, what we want to do is a little different. We want this to be more informal. And so my presentation is actually going to be quite short, but I want you to be more, to participate more. So what questions come to mind? I want you to enter those in the chat box there, in the Q&A box, so that we can talk about those. If you were the one that had the mic today and were addressing the participants, what would you like to say? What comments would you like to make? And so we want to invite you to submit questions and submit comments so that we can have more of a discussion rather than a presentation. And like I say, this is much more informal. Helping me out today is Francisco Diego. He's the product manager for RAM Connection and RAM Elements, and he's going to help me field those questions and those comments. So let me jump right into it. There's a lot of concern today with how software has become more complex and complicated, and particularly how the codes themselves have become more complex and complicated. And there's always a fear of, am I doing this right? Is my software doing it right? Am I getting appropriate answers? And so there's a lot of concern about that accuracy. And so I want to talk about some of those things just to get you thinking about what it is you need to be thinking about. Now I want to start out right at the front. I want to make a comparison of some finite element analysis results. And I'm going to compare 3 different programs and the results that they gave, in particular for this structure right here. Several stories tall, concrete moment frames with concrete shear walls. And you can see the layout. And so typically in software, the analysis is done by finite element analysis. Often people think of finite element analysis to mean, the plates and the meshes and whatnot. But beams and columns, they're also part of the finite element analysis. So this is the textbook that I used back in 1981 or 1982. The concepts of finite element analysis have been around for a long time. And the first edition of this book came out in 1974. So these concepts are well established. They have been tried and tested over the years. And what you're going to find is that most of the software, if it's been developed by responsible individuals, you're going to find very similar answers because, at least with the basic finite element analysis, because these concepts are so established and so common. So let's take a look at the results from this particular model that's been subject to an analysis. Just a basic analysis, no P delta, no response spectra. This is just a pure lateral and gravity analysis on this structure. I want to direct your attention first of all to the building periods. So here I've listed the first 3 building periods, the periods for the first 3 modes of this structure, and I'm showing the results from RamFrame, STAAD.Pro, and another software. I'll just call it BrandX. It's a major software out there, and if I told you what it was, you would instantly recognize it. But for the purposes of my presentation, I'm just going to refer to it as BrandX. Well respected, highly regarded. If you look at the results, for example, for period 1, T1, you see that RamFrame selected a building period of 0.6469. BrandX determined a period of 0.6509, and STAAD.Pro selected a period of 0.64. And the printout was only to 3 decimal places, and so that's why I'm only showing the 3 decimal places. You can see the difference between RAMFrame and that other software is only 0.004 of a second different on the primary period. And that's not surprising that the answers are that close. And it may be that they diverge even that much because there may be like a slightly different value used for E, or some material property calculation that's done maybe slightly different, could account for those differences. Look at the total reactions for the dead load and the live load, the unreduced live load. And again, the vertical reaction for RAMFrame is, well, for all three of them is 8,379 kilonewtons. This model happened to be in SI units. And the difference in the total reactions for all three programs is out there at the decimal place. So again, we see very close comparison between results. And then let's take a look at the column forces for column C1 of the first floor of that model, and we see that the axial loads and the moments and the shears, they all compare very precisely and nearly exactly. And again, this shouldn't be surprising. It's because that basic finite element analysis that's performed, we're essentially using the same techniques. We're using the same rules for finite element analysis. Now, where it does get different is the implementation of special analysis options, such as, how does the program handle p-delta analysis, for example? How does it handle live load reduction? How does it handle response spectra analysis? So that's where you'll begin to see differences in results, but more particularly, that's where you need to really make sure you understand what it is that you need to input and how you need to specify those, because that's where the criteria and the options that you're presented with become important. I want to show the comparison for another model. This is this two-story building, and it's got semi-rigid diaphragms. So in the semi-rigid diaphragm analysis, now the floor is going to be meshed. It's going to take into account the floor properties, and what we're going to compare is the building periods to see how closely the programs compare. And in this case, I'm comparing RAMFrame and that other program. And what I want you to pay attention there to is the listing of the periods that I've pointed to with the green arrows. So for the first mode, the period given by RAMFrame is 2.0278, and for the other software it's 2.0283. So we're out there at the fourth decimal place. We're off by 0.0005 seconds on this rather complicated model when you consider that it's meshed the whole diaphragm. Just a note about the displaced shapes. You'll see that for the first mode and the second mode, the displaced shapes are drawn and they look the same. And then after that, they seem to diverge. And the reason for the divergence is because when you're calculating mode shapes, the shapes are normalized, and RAMFrame chose one sign convention and the other program chose a different sign convention. So what you're seeing there with the differences in the graphics is they're just moving in different directions. But that's a mode issue, and the signs really are irrelevant, because we could multiply the one set of mode shapes by -1 without changing the answer, and then the graphics would have been the same. So I just wanted to note that the reason the graphics look different is just merely because in the one program the sign convention is opposite from the other in terms of how they draw that. But the periods compare, once again, very, very similarly. And so with some very quick model creation, you can take a look at what your software is doing, strip out all of the advanced analysis stuff, do the basic analysis, get comfortable with that, and I'm confident that what you're going to see is very favorable results. And then you need to then understand, how am I going to do the more advanced kinds of things? What are the criteria? What are the methodologies that are used? And I'll talk a little bit about that. And again, I'm not getting any questions or comments coming in. If you have any questions or comments, please feel free to submit those, and we'll talk about those. And you don't need to wait until the end. If something comes up while I'm speaking, if it's relevant to what I'm talking about, I'll take the time and we'll talk about it and extend the conversation. Otherwise, we'll wait till the end. While we're talking about diaphragms, there's an issue with diaphragm slabs and shear wall mesh sizes. And it's commonly felt that the smaller the mesh is, the more accurate your answer is going to be. But that's not always the case. And here's a real practical example of, I have an area here where there's a very high stress. And if I make my mesh smaller and smaller and smaller, and then I look at the individual mesh results for shear, for example, the stress value is going to, it may very well increase as I get a smaller and smaller mesh size. And if I just look at a single very small mesh and I look at the shear for that mesh, that might indicate that this slab is incapable of handling that mesh. But the reality is that the concrete is sharing that stress over a larger distance than that very small mesh. And so the small mesh giving the higher stress concentration for a diaphragm or slab or a shear wall may very well give values that are not accurate for design, but rather the larger, more regular mesh would give you answers where that shear stress has been spread out a little bit more, and those become more reasonable results. And I can't give you any rules of thumb at this point. We'll use a mesh of this size or that size, although I do have a personal recommendation or rule of thumb that I use. But if your smaller and smaller mesh is giving you these higher and higher values, you need to take a look and see if that small mesh really is giving you the design values that are appropriate for what you're trying to design. So I want to move on to another subject here. And again, now this is an area where different programs implement response spectrum analysis differently. And you need to understand what the program is doing, and you need to understand what the limitations are, and you need to have a feel for what you need to do to fill the shortcomings, because there are some shortcomings to the response spectrum analysis. So I'm using this building shown on the left, and the lateral frames part of the building is those frames shown on the right. Moment frames in the X direction, and brace frames in the Y direction. And so this is the model that I'm going to use for this response spectrum analysis. So first of all, let's take a look at our periods, and then we'll talk about how that relates to response spectrum analysis. So the primary period, if I check the periods with P delta turned on, and ASCE 7 and other building codes would require that you perform an analysis to include P delta. But if I include P delta and get my periods, then you can see there on the left that my primary period is 1.5897 seconds. If I fail to do P delta and calculate my periods, I actually have a shorter period of 1.5316. And the reason the period is shorter without P delta is because the P delta effects tend to lengthen or soften. They soften the structure and they extend the period of the building. So when you properly apply P delta in the calculation of your periods, you're going to end up with a longer period. So you're going to end up with different periods with P delta versus without P delta. Now, a shortcoming of the response spectra analysis method is that if your P delta analysis is an iterative P delta analysis method, it's incompatible with the response spectra analysis. So if your software does the iterative approach, then when you go to do response spectra analysis, you have to run it without P delta. But if you run it without P delta, you're going to end up with incorrect periods. And so let's take a look and see what impact that has on the base shear, for example, that's given by a response spectra analysis. So here we see the base shear with P delta turned on and base shear without P delta turned on for a response spectra load case. And RamFrame has the ability, because it doesn't use the iterative P delta approach, it uses the geometric stiffness approach, which is not an iterative approach. RamFrame has the ability to run a response spectra analysis with P delta turned on and without P delta turned on. And so I'm able to create these two reports so that we can see a comparison. So in the response spectra analysis, where P delta is included in the analysis, the base shear for the dynamic load case, that's the plus eccentricity case in the x direction, the base shear is 156.41 kip. But if I do that same analysis and I turn off my P delta, then my base shear drops to 149 kip. And so we can see that there's a difference whether P delta is turned on or turned off. And you know, the comment is made and it's valid. Well, we're going to scale our base shears to match the effective length method anyway, so our base shears are going to end up the same.
Alan.
And while that's true, the thing...
Alan, sorry to interrupt you here. There's a good question here.
Yeah, go ahead.
About the geometric stiffness approach. The question is if that's what you would generally use in place of an iterative P delta analysis.
That's a good question. That depends on what your software does. I think traditionally people have held the iterative P delta analysis in higher regard than the geometric stiffness method, but as my presentation shows, there is value to the geometric stiffness method. And so I'm not saying that one method is necessarily better than the other. At the same time, I'm not saying that one method is worse than the other. What I'm presenting here is at least an alternative approach to the iterative P delta that does have some value, and here's the value. In this case, we can do a response spectra analysis either with or without P delta, whereas if you have an iterative, if your software only does the iterative approach, then you can't run the response spectra analysis and do P delta at the same time. And the specification requires that you do P delta. And so it's ironic, the code in some cases is requiring a response spectra analysis. And the reason it's requiring it is because you have a building, for example, that's torsionally irregular or has some sort of irregularity. And so what the code says is that the equivalent lateral force method is no longer accurate enough. We need something more accurate, a more accurate analysis, and we're going to require a response spectra analysis. So now we're going to do this response spectra analysis, which potentially loses accuracy because now we can't include p delta if the software doesn't accommodate that. So there was a follow-on question to that. So what do you do if you have an iterative analysis, if that's what your program does? And I'll get to that in a minute. We can talk about how you can still use an iterative analysis and still get the results that you need. So back to my comparison here. The fact that the base years are different also should signal to us that also means that the distribution of this base year in the structure is different, whether we've included p delta or not p delta. And certainly with the structure where there's a lot of torsion going on, a lot of redistribution going on, what we will see is that whether you have p delta turned on or not does have an impact on those results above and beyond just the difference in the base year. So here we look at column number 12 in this particular example, and we want to take a close look at the moments, both when p delta is turned on and when p delta is not turned on. And again, we see a difference both in the axial force and in the moments in the top and the bottom of the column. And the ratios of these differences, it's not the same as the ratio of the differences in the base year. But these differences, these ratios are all different because of the impact that p delta has on the moments in a member. And so that's something that's important to remember. If your analysis, if your p delta analysis is based on an iterative analysis approach, and therefore it's not included in the response spectra analysis, a recommendation that I've seen given is to apply the B2 factor. And so that's certainly an approach that could be taken here. And so in this case, in this model, at this level of the structure, the B2 factor is 1.08. So if your lateral analysis is based on an iterative approach and you're doing a response spectra analysis, one solution to the dilemma is merely to calculate the B2 factor and apply the B2 factor to the moments, and then you've satisfied the requirement for response spectra and you've satisfied the requirements for p delta. Again, it's a little ironic that the reason we're doing the response spectra analysis is so we can be more accurate in our analysis for these irregular structures, and then we're sort of hampered with having to apply a B2 factor that's based on a very approximate methodology. But that is a solution, and it's a reasonable solution. But again, it's important that you understand what does your software do, what's it including, what's it not including, and what steps do you need to take to alleviate that problem. So let me go turn to one final example, and then we'll really jump into the questions and the comments that we're getting. So ultimately, the purpose for all of this analysis is so that we can come up with a safe and proper and appropriate design. And oftentimes we feel like we need to spend perhaps even an inordinate amount of time in our analysis, making sure that our analysis is very precise and very exact, and get it right down to the degree of of accuracy that we're comfortable with. The thing that's interesting is when we go to actually do the design, some of that accuracy becomes, to a degree, irrelevant. And let me explain why with a couple of examples. So this is taken from the AISC Still Manual, and it's a list of the plastic section moduli for all of the W shapes. And listed in this table are what I will refer to as the common sizes. So the sizes that are listed in bold in this table are the common sizes, and if you look at it, you'll recognize, yeah, these are the shapes that really are typically picked in the design of a structure, these that are highlighted in bold. What I did was I took that list of those common sizes, and I'm listing their PMP, which is their moment capacity, assuming that the beam is continuously braced. And so I'm listing the capacity of these common shapes. And then in the third column there, the rightmost column, I'm listing how much the moment capacity is changing from one shape to the next. So for example, at the very top we see that a W24 by 84 has a capacity of 840 kit feet. And a W24 by 76 has a capacity of 750 kit feet. And the change between those two is 12%. And if you look down that third column, that rightmost column, you'll see that as we go from common shape to common shape, there's a big jump, there's a big jump in the capacity of those shapes. So what that means is we go to all sorts of work to get our analysis just perfect. And then when we actually go to select a beam size or a column size, it's not like we're picking a beam size or column size that exactly works for that demand, but we're picking something that may very well be 10 or 15 or 20% even higher capacity than what's required, merely because that's what's available. That's what's made. And so I don't want to be misunderstood here. I'm not advocating that we be sloppy in our analysis, because we need to be accurate, and we need to put in the appropriate effort. But always keep in mind, if we are starting to go into too much effort to get precision, that effort may not be warranted, because in the end we're going to pick sizes of which there are, distinct jumps in those capacities. Concrete designs is very similar, and what I've done here, let me explain this table. On the left, I've listed, for example, the sets of bars and the area associated with that. And so, for example, two number 5 bars have a combined area of 0.62 square inches, and two number 6 bars has a combined area of 0.88 inches. And if you go down, 6 number 5s, for example, has an area of 1.86 square inches. So if we order these possible bar selections, 2 number 5s, 2 number 6s, 3 number 5s, 2 number 7s, etc., and order them by their area, then what I've done is I've listed what the percent of increase is in the area between the one set of bars and the other. And so the jump between 2 number 5s and 2 number 6s is a 42% increase in area of steel. And from 2 number 6s to 3 number 5s is a 6% jump in the area of steel. So you can see, in the case of rebar, it's a finer jump than it is for steel beam sections, but there still is a jump, 11%, 3%, 8%, 9%. So we go through all this effort of doing an analysis, but when we finally go to actually do the design, we're picking bars that isn't exactly, usually doesn't exactly satisfy the demand. There's that jump there. So again, my point here is don't get carried away with precision. Make sure that your efforts are reasonable, because you do want to be correct. You want to take the time and effort that's required to come up with an appropriate design. And if you're doing something that's always 5% unconservative, then on average, your designs are going to be 5% unconservative over time, over many structures. Likewise, if your approach is always 5% conservative, then over time, on average, your designs are going to be 5% conservative. So you do need to be careful and put in the appropriate effort, but we need to be careful not to get carried away with the idea that we have to be exact and precise in everything that we do. So I just want to give you a pitch for an upcoming webinar, an actual webinar where I expand on what I've talked about here. There's a webinar in August, and the title of that is Accuracy, Precision, and Practicality in Structural Analysis. And I give more distinct examples, and I talk about this whole issue of what's accurate versus what's precise and what's practical. So hopefully this will give you some ideas to think about, but in that webinar in August, I'll go to a much greater length in describing some of these things that you need to watch out for. And I'll give some pointers on some things where you might run into some errors if you're not cognizant of what your software is doing and what it's expecting. So with that, that's the end of my presentation. I hope that what I've presented is has invoked some ideas and some thoughts. Feel free now to ask any questions, make any comments, contribute to the discussion. I'm going to turn now to Francisco. Francisco, have you got some questions lined up for me there?
Yes, there's some follow-up on when you were talking about P-delta and response spectrum analysis. There's a follow-up question on that. If there is another option, I mean, you mentioned that if you're running a response spectrum analysis, iterative P-delta is not a good option. So what would be another option? Or is that the only option, for example, in RAM-frame?
In RAM-frame, the geometric stiffness method is one option. The B2 method is a second option. RAM-frame doesn't do the iterative analysis. Most programs do the iterative analysis, and I would suspect that they also offer the B2 method. And so I think most software has the options that the engineer would need, and they just need to take a look and see, is it giving me the accuracy that I want, or do I need to look at something else?
Very good. And then the other one would be if you're running a geometric stiffness approach, this is usually based on a single load case. So if that is the case in RAM-frame, what would be that load case, or if it's a load combination? And the follow-up question is if this doesn't underestimate P-delta effects because you're including lateral loads like seismic or wind.
So keep in mind that we're looking at the global effects, the global P-delta effects from the structure. And certainly an individual member or frame, everything undergoes this P-delta effect. But in the case of earthquake, for example, for every downward acting force in a column, seismic force, there's a corresponding upward acting seismic force in a different column in the structure. And so when we're trying to determine this P-delta influence, what we need to do is we need to soften the structure, or we need to consider this load case of dead and live. And then when the earthquake hits and it's applied to any given member, then those P delta effects are taken into account in the structure. Trying to think how I can explain this more clearly. Again, this P delta on a structure, it's a whole structure effect, and in the case of seismic forces, there's uplift as well as downward acting loads, which on the structure as a whole, they counteract. Wind is the same, and typically you have wind uplift, which means your P delta is even actually helps your P delta because it's pulling your columns into tension. Now, if you had significant a net downward acting force due to wind, then in that case, yeah, you should take that into account in your P delta analysis. So let me explain what ram frame does. With ram frame, it takes the dead load, the entire dead load on the structure, and it takes the entire live load on the structure, and it applies the factors specified by the engineer, and those factors usually would correspond to what's going to be presumably the controlling load case. For example, 1.2 dead plus 1 point live plus seismic. So we're going to consider 1.2 dead and 1.0 live. It takes the total dead and live load on the structure with the live load appropriately reduced based on the live load reduction, factors it based on those factors, and then calculates a softening of the structure, which is the geometric stiffness, a softening of that stiffness, and then in the analysis for all of the load cases, dead, live, wind, seismic, it's applied that softening. So when the earthquake hits, it's hitting a structure that's been softened due to the effects of the vertical loads creating those P delta effects. And so as the structure sways and the axial load in the column from the earthquake hits the column sways, there is a P delta in that column due to the seismic force, the downward acting seismic force, that's included in the moments in the column. And so that P delta effect of the axial load in the column is taken into account. But that gets back to the original question, why are we looking at dead and a percentage of live when we're calculating these P delta effects? It's because those are the vertical acting forces on the structure as a whole.
Good. There's another question here. I think it's more general, not so technical. And it's talking about our two products, the ones you mentioned, Stat Pro versus Ram Frame. And since they're both Bentley products, the question is, which one would you recommend? And I believe this is more than, it depends on the type of projects you're addressing, right? The right tool for the right job. But I'll let you expand on that. Okay.
Yeah, and I think that's the right answer. It depends on what kind of structures you're analyzing. And even though RAM and STAD have different approaches to the P delta analysis, again, I'm not saying that one is better than the other. Each of us chose the method that we did for particular reasons. So in the case of a building structure, the geometric stiffness method works out very well. And it has a lot of advantages. You can analyze load cases, and then you can combine load cases into combinations. Whereas with an iterative analysis, you can't do that. You can't iteratively analyze a dead load case and then iteratively analyze a live load case, and then later combine them in load combinations. If you're doing the iterative P delta analysis, you have to iteratively analyze the load combinations. And there's pluses and minuses to that, and I don't have a lot of time to go into that, but just highlight for RAM frame, for the RAM structural system, we selected the geometric stiffness method because it works well for building structures, and it gives some advantages in terms of the complexity and the reporting, and the fact you can do an analysis and then you can go off into the foundation module and then combine your combinations appropriately for the foundation module. You can go into RAM concrete and create your combinations there appropriate for concrete design. Go into the RAM frame steel module and do those that are appropriate for steel. Rather than having to analyze all of these load combinations all up front and then going off and doing the associated design, we can do them as we need them. We can create the combinations as we need them. So that's an advantage of the geometric stiffness method. Now, STAD is more general purpose, and so you might do a tower, you might do an arch, you might do just a truss. And for those, the geometric stiffness method is not appropriate. And so STAD would have been very limited had it merely implemented the geometric stiffness method. And so for STAD, for the kinds of structures that it typically analyzes, I would suggest that the iterative analysis is more appropriate. Now, if you're using STAD and you're doing a response spectrum analysis, no matter what kind of, whether it's a building or industrial facility or a tower or whatever, keep in mind that you do have to decide, how am I going to handle the P delta effects, or are they significant? But again, it's a matter of, I'm not saying one is right and one is wrong. That's not the case at all. It's just a matter of, I'm just saying, whatever your software does, make sure you understand and know how to deal with all of these requirements.
Excellent. Another question here is if you could comment something on common pitfalls on mixing different materials for the lateral systems, right? Like concrete and steel. Any recommendations you can give them on mixing on a example? The one you showed in the example is all concrete, but what happened if you had lateral steel frames in that one, for example?
So I'm trying to think what might be an issue. Typically, all of the programs would allow you to mix materials. You could do an analysis. I could do a response spectrum analysis of a structure that's a mix of steel and concrete. If you look in both the steel code and the ACI code, they both have a B2 methodology. B2 is what the steel spec calls it. I can't remember what the ACI code calls it, but it's the same thing. It's that large P delta moment magnifier. So if you look in the ACI code, there will be a section on moment magnification, and it'll talk about the B2 factor. So even if I have a mix of steel and concrete, and if I need to apply the B2 factor, that large P delta factor, that moment magnifier, I can do that because both concrete and steel have those requirements. So again, you just be aware of that. I hope I addressed the question there. If not, if the person that submitted that could clarify that and send it in, I'd be happy to see what I can do. So there's a question here that I want to take a look at. The question was, P delta effects represent a softer structure, hence a longer period. Why is the base shear larger? So let me go back and take a look. So, I mean, that's an interesting question, and normally I would expect in an equivalent lateral force analysis, what we would expect is if the period is longer, the base shear is going to be smaller. And we're not seeing that here. What we're seeing here is this response spectra analysis has a larger base shear with P delta than it does without P delta, which the attendee observed seems to be counterintuitive. And I would suspect that the cause, again, is the structure with P delta probably has a mode that is closer to a resonating mode, to the earthquake that's being applied. And so if a particular mode goes into resonance with your earthquake, then that mode is going to have more dominance, and the forces that result from it are going to be higher. And this is a good case where ignoring the P delta in the response spectra analysis can have an effect that's counterintuitive. I suspect, like I say, it has to do with being more closely attuned. The building with the P delta effects being considered, being slightly softer, put them closer to a resonating mode from that earthquake, and hence the higher forces. I think that's probably what's going on. And so again, it shows that not including the P delta in your analysis can have an effect on the base shears. It can have an effect on the distribution. But in the end, if your analysis didn't include the P delta analysis and you applied the B2 factor, the B2 factor is going to be the B2 factor is going to be conservative, and so I think you're going to be covered. I don't think there would be a problem with applying the B2 factor and feeling confident that you've covered the requirement. There's just one quick question here asking about the building period. And the question is the building period the first mode period, or is it the average from all the modes? And the building period that we were looking at in this report, it's the first mode period. It's the fundamental mode. So the fundamental mode in the it's the x direction in this case. The fundamental mode in the x direction is 1.5897. So that's the first mode's period, which is the one that's typically the dominant one. So when we're looking at equivalent lateral force, that's the period we're using. It's from the first. It's from the first mode. It's not some average of all of them. We wouldn't take the average of all of them and use that average number. And then somebody also referred to my B2 factor of 1.08. That was just for this building. So you need to run the analysis. You need to go through either the AISC Appendix 7 or 8 indicates how to calculate the B2 factor, and the ACI specification indicates how to do the moment magnifier. You need to go through and perform that for your structure, and keep in mind that that number is going to change at every story, because or potentially it's going to change at every story. And so you need to go through a calculation. Often that number is pretty small, 1.04, 1.05. If you have a particularly soft structure, then you can see some higher numbers. And if you start to see higher numbers, like in the 15, 1.15 or 1.2, you might want to think about stiffening up your structure. Because what that represents, that B2 factor of 1.08 that I used for this particular model, that I calculated from this model, what that means is that potentially the moments in the members are 8% higher when we consider the P delta effects than when we don't. And that's what that B2 is attempting to measure. It's attempting to measure what would be my moments and my design forces if I include P delta versus not including P delta. That's what it represents. And so you need to calculate that for each given structure, and as I said, for each given story. Somebody has a question in regard to approach that is sometimes, that I've heard is sometimes used, and I've never done this before, but the question is it reasonable to run an analysis that includes P delta effects for all the other load cases that are part of the seismic combination, and then combine the results with response spectra analysis of the lateral loads? So I would assume that would mean run the 1.2 dead plus 1.0 live, run that with the iterative solution, and then combine that with the results from the response spectra analysis. That would give you a closer answer, but you would still miss the effects that P delta have on the seismic forces. Back to the overturning on a column, you've got the vertical load from the seismic load hitting this column, and that approach would miss the additional moments induced by those P delta effects on that vertical load acting on that column. So you'd be closer, but you'd still be missing those P delta effects in that portion of your analysis, and now it makes it harder for you to know how do I modify the response spectra analysis load case to include that. If you're going to use the B2 factor, I would just do my normal analysis and then apply the B2 factor to all of them. But having said that, I'm not sure. Now I think about it, so then you just apply the B2 factor just to the response spectra analysis case. You wouldn't apply it to your dead and live because you already took those into account. I suppose you could do that. I haven't done that, so I'm hesitant to endorse that one way or the other. And somebody did make the comment for large structures with thousands of elements, the B2 factor looks very painful, and yes, it can be. Although I think in most cases you can calculate a B2 factor for a story and then apply it to all the members on that story. The way the B2 factor is calculated, and at least that's for a building. For something that's more exotic than a building, then that would become more difficult. Let's see, Francisco, can you see anything there that we might want to elaborate on?
No, I think some of the questions we can address afterwards, they seem very particular, so we can contact the users in particular and respond and have a chat with them. I see an interesting one, not technical. Will this session be available later for people that missed it? I mean, is there going to be a recording or? And I believe the answer is yes.
Natalie will have to answer that one. I
Exactly.
believe it is
So
being
it will
recorded.
be available on YouTube later. Our YouTube channel.
Yeah.
I think those are all the questions, Alan.
Okay. I really appreciate this opportunity to have this discussion. I hope it was worthwhile. It was, like I said at the beginning, it was a different format. It was a little more informal, which certainly puts us on the spot here to try to answer the questions as they come up. I would appreciate feedback, and so if you feel free to contact us and let us know what you felt about this. Was it, you just spent an hour of your life, was it worth it? Was there something that we could have done different? Is there something that we could have done with greater focus? And so we would appreciate feedback on how effective this even was today. But again, I really appreciate your attendance, and I'll turn the time back over to Natalie.
Thank you, Alan and Francis.